Okay. So far, so good? Now, what happens to this? How could this change? So what do you think? Can I increase the number of scatterings per second? How do I increase or decrease them? Can we think of what we could do?
Velocity.
Good. We could increase the velocity. What else could we do?
Increase the number, like the n.
We could increase the n. Can we do something else?
Increase the radius.
Well, no, the radius of the particle, well, yeah, I mean, that means we'll have to change the particle. But if we don't change the particles, we keep them the same. Can we change both? Can we change the speed and the n? Right?
Yeah.
So if we, what?
Change pi.
That would be a miracle. Yes, that indeed would be a miracle. But no, let's not change the pi. But we could change the number of particles that are hitting, so scatterings will go up. We could change their speed, so it's just that the fact that there are more collisions per second. Or we could change both, or we could decrease them. So that's how we would change it. So the changes that could happen would be n, could be speed, or could be both. And why does this happen? Even though the particles themselves did not change. Not necessarily. We're just increasing the likelihood of interaction. Remember that word? The word we defined in the beginning? We're just increasing the likelihood of the event to occur. That's all we're doing. So then instead of talking about the number of scatterings per second, I have to redefine it slightly. And instead I have to talk about this term, scattering effectiveness. What is scattering effectiveness? So mathematically, it is defined as scattering rate. What is rate? Yeah. The change, the derivative. Scattering opportunities. So the rate is what? Scatterings per second? Is that how we define rate? And it's a derivative, it's the change, divided by what is a scattering opportunity. Scattering opportunity in most textbooks is written as the incident flux. What is a flux?
The amount of, like, it's over some kind of area, like how much you move.
That's the difference. So there are initial particles, but when you're talking about flux, it's the ones that are perpendicular to whatever the area you're looking at. Okay? So there could be other particles in that tunnel that say, so the tunnel isn't defined as, remember when you were talking about the tunnels and fluids? And we said they were fluid flow tunnels that go through. There could be, like in this case, there could be particles that are coming this way and that way and all kinds of ways. But which ones are we fundamentally interested in? The ones that form the flux to it. Okay, so in other textbooks, you will see the scattering opportunity being defined as the incident flux. So do you want to write that down so we don't forget? Incident flux. Make sure I don't misspell stuff. And incident flux is defined as, so I'm just going to do scattering per second, divided by number of incident particles that come in the impact area per second. So far, so good? Now, what would that be? Scattering per second. We had scattering per second somewhere. We just derived it. Can you find it? It's on this page somewhere. What should I replace scattering per second?
That's the N by R thing times V.
For 1 second?
Yeah.
Divided by the number of incident particles times their speed. How fast they're going. Right? They're coming in that impact parameter. N goes away, V goes away. What are we left with?
The area.
So
Yeah, this
Oh,
person.
yeah, because it's person.
scattering effectiveness is then nothing other than pi r plus RH squared. And you have seen this before if you've done quantum mechanics. Do you know what this was called?
Oh, sigma.
Sigma for scattering. And the fancy word for this was cross section. But that's literally all that means. Yes, sir.
Why the instant flux also have speed?
So remember we said that the two things that could increase were N and V. So you have to account for both of them when you're talking about scattering effectiveness.
As we're survived by
Yes. So if N changes, the scattering effectiveness changes. If V changes, the scattering effectiveness changes. So the incident flux, when you define it, you have to take into account both of those things. Right? But isn't that amazing? Oh, and by the way, you will see this term written as total cross section. So why is this a good idea to know? And how does it help us? How do you think that people found the R's of different particles that they can't see? Cross sections. Because look at it. If you can tell me what the scattering effectiveness is, I can tell you what the R's are. Because the impact parameter tells me what each of these things are. So we do not know R's of particles, right? They're tiny, we don't know that. And they're in a beam, so I can't isolate one. But if I can only find the impact parameter, which I can find if I know the total cross section, I can tell you what the R's are for the different particles that I can't see. So initially in the early 19th century, there were a lot of experiments that were done to figure out what the radius of the hydrogen atom is, what the radius of the nitrogen is, what the radius of, you name it, they figured it out. What else do you think this could help us? We could do this to compare what we think the radiuses are versus what they actually are. We can reconfirm that and all kinds of fancy stuff.